Hey everyone, welcome back, and today let's solve LeetCode problem 2900 titled Longest Unequal Adjacent Groups, Subsequence Part 1. So we're given a string array words and a binary array groups, both of length n, where words at index I is associated with groups at index I. Now our task is to select the longest alternating subsequence from that input string words, and a subsequence of words is considered alternating if for any two consecutive strings in the sequence, their corresponding elements in the binary array groups differ. Essentially, we are to choose strings such that the adjacent elements have non-matching corresponding bits or values in the group's array. Formally, we need to find the longest subsequence of any array of indices from 0 till n minus 1, denoted as I sub 0, I sub 1, up until I sub k minus 1, such that groups at I sub j is never equal to groups at I sub j plus 1 for each value j in the indices that we choose from 0 to k minus 1. And then we find the words corresponding to those indices in the actual input array words. And we want to then return that selected subsequence, not just its length or its indices, we want to return the characters themselves, and if there are multiple answers, we do have the liberty to return any of them. Note that note that the elements in the words are always going to be distinct. It's only going to be their groups that could be duplicates, and that's what we have to really consider when choosing the most optimal sequence of elements. So in example 1, we have our input array of string words to be EAB. As you can see, again, they all differ, and our group's input array is 0, 0, 1. Effectively, the reason why we have an output of EB, as that is the longest length of 2, that is still a valid subsequence of the input array words that we can return. The reason why is because if we really analyze this output here, E is going to be mapped to 1, or rather to 0. Why? Because words that index 0 is equal to E, and groups at index 0 is equal to 0, and so E is going to be mapped to 0. It's kind of like going through the zip of these two input arrays if you're using Python, right? A is going to be mapped to 0 as well. We can't have E and A next to each other because they do have the same exact group value. And since they are actually adjacent, E and A, and they do have the same group, we can't put them next to each other in our output. If we go to B, we see B is mapped to 1. That's great. B is mapped to 1. 1 is different than 0, and since in this case B and E are adjacent in our output, and they are mapped to 1 and 0 respectively, which are different, we can actually have that as our output. Now note that another valid kind of variation or combination to choose would be A and B. A and B are mapped to 0 and 1 respectively. They still follow that subsequence property. They're both adjacent with different group numbers, and so that also has a maximum length of 2, which would still be a valid output, and so EB would also work along with AB. In example 2, we have our input array words of strings to be A, B, C, D, and our groups are going to be 1, 0, 1, 1. In this case, the most optimal kind of choice we can make here is to choose this A, this B, and then this C. Just very directly, the first 3 characters in our input array words. Why? Because that's going to be the longest alternating kind of sequence, or subsequence, if you will. Because A is mapped to 1, that's cool. B is mapped to 0. They're adjacent, they have different groups, that's great. We can include them both consecutively in our output. C is actually also mapped to 1. That's also great. Why? Because 1 is different from its adjacent left 0. And since C and B are in different groups, we can also put them two together because they are actually in alternating groups. And so A, B, C is valid still, right? Every single adjacent element is different, is in a different group rather than its adjacent element. Right, so ABC is the longest subsequence of indices that still satisfies the condition. So for the constraints here, we see that n is going to be equal to the number of words, and it's also going to be the number of groups we have, and that value n is going to be between 1 and 100, indicating that we have rather small input constraints. Any value in words, basically words.i.length, basically the length of any word is going to be between 1 and 10, and groups at index I is either always going to be 0 or 1. It is guaranteed to be a binary string, like the problem statement also confirmed to us. Words is always going to consist of distinct strings, and it's always going to consist of lowercase English letters, kind of just validating the problem statement and telling us that we're always going to have valid input arrays, if you will. Which leads us to what is a kind of efficient way and main observation to note to help solve this problem efficiently? Well, the first one is actually that, look, whenever we're trying to find the most optimal subsequence of characters to choose from our input array words, there is no reason why we shouldn't always choose the first element. Let's go ahead and look at why that really is. In example 1, we chose E and B. E is indeed the first element. We chose it. It's still optimal, right? Now, granted, A and B would also work. That doesn't make it more optimal. They're both equally as optimal, and so we'd always want to kind of choose the first element. Why do we want to always choose the first element when we're trying to make the most optimal alternating subsequence? Let's go ahead and confirm that in example 2 first. We have A, B, C. Guess what? That's also including the first element. In fact, it's including the first 3 elements, but that's irrelevant. We only care about including the first element in our most optimal subsequences. Right? Why is that? Well, let's go ahead and look at a few examples to kind of just prove why that always works and why it's a more optimal solution. What if our groups array was 0, 0, 1? This is kind of mirroring example 1. I could pick the last 2 indices and skip the 0th one. I could get 0, 1. That has an optimal length of 2, which is indeed the maximum answer. I could also include the first index and pick this 0 and this 1 from our input array words, which would still be valid. Okay, that's fine. What if I had something like 0, 1, 0? Let me think here. What if I just skip this? This is still different than this, right? And those two are indeed adjacent. And so I can just go with 1, 0. But guess what? Since these two indices are also different, I can include the 0 as well, right? So even if my first 2 indices are equal, choosing the first element is never going to get me in trouble, if you will, right? Because even if I had more elements here, that wouldn't really change anything. That would just be adding on to this. We'd still have 0, 1, 0, or 0, 1, 0, regardless of which 0 we choose. 1 is never going to be suboptimal. It's always going to be the most optimal, right? The first index. And same thing here. Even if the first 2 indices are differing, they're not the same value. Still, if they're not the same value, that works even better. We can include them both because they are actually alternating. And so we can pick 0 and 1 and include any elements after more optimally, right? Or greedily, if you will, right? Which leads us to that main observation. Choosing the first index or the first character in our input array words is always going to be part of that most optimal solution, right? Even if the next index is equal to it or adjacent or alternating or different than it. It's always going to lead to the most optimal solution and never the least optimal solution regardless of what that is, right? So how are we going to solve this problem? Effectively, it is really just a left to right scan of our input array words, kind of using that kind of knowledge of what the problem statement says. We always start from the initial character and build our way up from there. And effectively, whenever we find an element that is differing in group value than the most recent element that's adjacent to it, we always try to include it to be as greedy as possible and go on from there, adding on elements with different group values that are adjacent to each other as we scan through them from left to right in our input array words. So let's go ahead and code the solution. It is rather simple, especially when compared to yesterday's very hard problem, and it is kind of a sigh of breath or belief that this is an easy problem. It's nothing too hard, right? So let's go ahead and get into the solution here. The first thing that I'm going to do is actually initialize my result. This is going to be the list that I end up returning. It's going to be the list of characters that are in my input array words that are part of that alternating subsequence where all the adjacent characters in this resulting list have different group values, and they all still are in the input array words, and they still have that property of a subsequence, because if we iterate from left to right in the input array words, whenever we include elements, even if we include all of them or none of them, we're guaranteed that the ordering of those elements are still going to be maintained, the relative order that is, and so that it is still going to be a subsequence of our input array words if we iterate from left to right, right? So let's go ahead and begin that, and before we do that, let's finally initialize a previous group. This previous group is basically just going to be keeping track of the group value of the most recent element that we've added to our final resulting list. And so for the next element that we consider adding, as long as it has a different group value from the most recent one, which is sorted pre-group, we know we can add it because that's going to be adjacent to the most recent one that we've added, and so as long as their group values are distinct, we can still add them as a valid input. And I'll explain that as we actually start iterating over the solution, right? So effectively, let's begin iterating over the input array words, rather zipping over both of them. And in Python, the way to do that is for every word mapped to its corresponding group in the zip, and I'll explain what that is in a bit, in the zip of words and groups. Right, so zip in Python is really just a straightforward method here that matches or maps every single element to its corresponding other element as long as they're at the same index. And since we're guaranteed that the length of the input array words and groups are always going to be equal, we know that there's always going to be a one-to-one mapping, or basically one element per group value. As we saw in all the examples here, E maps to 0, A maps to this 0, and B maps to this last element of 1, right? And if we zip through, or iterate through the zip of words and groups, basically that would be going like for every E to 0, and these would be in the form of a list, by the way, for every A to 0, and for every B through 1. Kind of like enumerating, where you're not just going through each value or word in the input array words, you're also keeping track of its group value along with that in each iteration as well, just to make sure that it is a valid element as we actually consider appending it to our resulting list. Let me just kind of put the code editor in so we can see this a little bit better. I think this probably helps. Now, the first thing that we have to check is if the current group value, meaning if group of the current element that we're trying to add, or rather of the current word that we're trying to add, if it's different or alternating, that's the key word here, than the previous group. And why do we care about the previous group? Well, the previous group is going to be the group value of the most recent word that we added to our resulting list. And so as long as the group value of the current element that we're considering to add to our result is different than the group value of the most recent one, we know we can add it. Why? Because the most recent word that we added to our result is always going to be the one that's adjacent to the current one, or the current word that we're trying to add. And so as long as those two elements groups are different, we know that they still can be added together. They still can be valid because their group values are alternating, and the way we can handle that is to append to our result this alternating group word, right? Because this word is going to have an alternating group to the most recent or most previous word before it that we've added, and that corresponding group. And so if that's the case, we can add the word to our result and then update the previous group to now be the current group's word, or rather the current word's group. And so it's going to be the group of the current word, because now the most recent word that we've added to the result is the current word itself in this specific iteration, and so that's going to be updated in prev group to the group of the most recent or current word that we're adding, and we're adding now to the valid word that has an alternating group to the most recent one to our result, and effectively returning the result once this for loop iterates, or rather once this for loop executes or terminates, which would eventually return the result. That would store the longest alternating subsequence of elements that have different groups and adjacent characters, or other adjacent words. So, unless I made any syntax errors here, this should be accepted. This should be a valid solution. And as you can see, this really is just about as efficient as you can get it to be. So again, on a high level, how are we really solving this problem? Effectively, we're starting from the first element and building our way up. We're monitoring the group of the most recent element that we've added, because that's going to be the adjacent word to the next word that we're going to potentially add. And as long as the word that we're currently adding is different from the most recent one that we added, as long as the word's group that we're currently adding, its group value is different from the group value of the word that we most recently added before this, which are going to be the two adjacent words if we do add them. As long as that's the case, the current word that we're potentially adding is going to be valid, even we can add it to a result, and then update the group of the most recent element that we've added this group to be the prev group of the current words group, and effectively return the result to store all the different characters with different alternating groups that are adjacent to each other in the resulting list as we added them, as we scan from left to right in our input array words, right? So for the runtime complexity here, since this really is just a single pass solution where we iterate over technically word and group exactly once, this really is just a fully simplified big O of n, or linear runtime complexity, where n is going to be the length of our input array word, also going to be the length of our input array group, as we saw in the constraints as well. And for the memory or space complexity, guess what? It's also going to be linear, or big O of n, where n is again the length. And the reason why is because at most, or at worst case, this resulting list could store all of the words in our input array words, right? Because what if every single word is valid? What if every single adjacent character has a different group value? Then in that case, all the words are valid. We can add all of them, and so that's worst case, adding all the elements in our words to our result. And so that's going to be big O of n worst case, and so it is going to be a linear memory or space complexity, or big O of n as well, right? So if you guys enjoyed the solution and there's something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye bye.